A particle moves such that its acceleration A is given by A is equal to minus bx minus bx it is within the reflection. So so A is equal to minus bx, where x is the displacement from the equilibrium position and b is a constant. So where x is the displacement from the equilibrium position and b is a constant. So clearly we are told that the particle's acceleration is a, b is a constant, and x is the displacement from the equilibrium position. Now, calculate the period of oscillation of this particle. Okay, so this is similar to you given the expression that A is equal to minus omega squared x. So when we compare, then it means that omega squared is equal to b of the particle. Because if you indicate minus, minus, they will cancel out. So omega squared is equal to b. Okay, and we all know that we can determine period from omega squared. We can all determine period. Okay, so I have Abba, Equia, Adomasha lot, Equia, Ama. Hey, Amira, this a contact is not a familiar. Please send me a hi if you have changed your gadgets. Okay, identification. Carl is here, Lynn, Maltiti, Natalie, and then Inshira. Is it Inshira Badankwa? Is it Inshira? Okay. So we know omega to be equal to 2 pi over t. So t is embedded within omega. So when we make omega the subject, we have square root of b. So that we have 2 pi over t is equal to root of b. Then make b the subject, t the subject. T therefore is equal to 2 pi over root of b. Professionally or mathematically, if you have a fraction and then the denominator is an irrational expression set, you have to rationalize it, eliminate the irrational expression at the denominator. Even though if you leave your answer in this form, you'll not be penalized. But when you have something like this, to rationalize it, you multiply through by root b over root of b. And by so doing, it's as if nothing is done to the fraction. So you have 2 pi times root of b over, what is square root of b times square root of b? Yes, anybody? So this is square root of b times square root of b is similar to root of b squared. And this will give us 2 pi root of b on b. So when you rationalize it from here, this becomes your final answer. But the answer can actually be this, or when you have rationalized it. Any question? No question. As for this question, a lot of you had it right. Many of you scored it. Question 2. A man measures the period of a simple pendulum inside a stationary left and finds it to be a T. So inside period, inside a stationary left is capital T. If the left accelerates upwards with an acceleration g over 4 seconds, then the period of the pendulum would be, so what would happen if the left accelerates upwards? So this is a left, a pendulum within. So when the left accelerates upwards, and J is equal to J on 4, meaning when it's stationary, there's no change in the acceleration due to gravity. But when it accelerates upwards, there is a change. Okay. Now, whenever a left accelerates upward, the net force acting on the left becomes, it is affected by gravity. So you have gravity acting on it, which is G. And its acceleration is going up. So the net force or the net acceleration on the left becomes, because it's going up, it means A is greater than acceleration due to gravity G, when the left has to go up. So we have the net equal to A minus G. Minus because you are looking for the difference between them. Negative G because we are moving in the direction against gravity. So this would decelerate. So the G becomes negative because we are moving against it. Please, are we okay? So A minus G. Minus because you are looking for the difference between them. Minus G because you are moving against gravity. So G is negative. Therefore, the net acceleration becomes A plus G. Are we okay? Now, the period of a simple pendulum is given by this. So this L is the length of the pendulum, and J must be the net acceleration. J must be the net acceleration, or L over G generally. So this would be the situation in the first, this will be the first situation. T1 would be equal to, or T, the first period, will be directly proportional to L over G. Then the second period, T2, must be directly proportional to square root of L. L will not change over the net acceleration in the second situation when it is moving. So A plus G. So if we take a ratio of T2 over T1, we have root of L over A plus G all on L over G. All on L over G. So the ratio T2 over T1 would be equal to L square root of L over A plus G times G over L. The length being common would cancel out. So let me clear the first part of the question and use this side of the board. And so we have T2 on T1 being equal to square root of J over A plus G. Then we are told that the acceleration, if the lift accelerates upwards with an acceleration G over 4, its acceleration becomes G over 4. So we substitute A for G on 4 plus G. And this would give us root of G on 5 G times 4. Okay, we have 5G divided by 4, but we'll go up to multiply. So we have square root of 4 over 5. So T2 on T1 becomes 2 over root of 5, because square root of 4 is 2, and then that's it. Therefore, the new period T2 becomes 2 over root of 5 of T1. This will be the second period. If it has to accelerate. To be very frank, I think this is a bit heavy for you at your level. Okay, but if you have still understood it, then please, that is a feather in your cap. But please spend enough of time to go over. All right, to master how to solve questions of this nature. Please, any question? Yes, Amma.
Sir, please, why didn't you rationalize the root 5?
Oh, we can. Yes. Yes. Thank you for the reminder. So, if we rationalize it here, we'll have times 5 times root of 5 times root of 5. So we have 2 on 5 root of 5. So that T2 becomes 2 on 5 root 5 T1. All right. So we can actually do that. Thank you. Then the last question. If the length of a simple pendulum is increased by 300%, then the time period would also increase by. This question is purely English language. If you don't pay attention to the English language, you'll get it wrong. But I think a lot of you also got this one correct. So we are told that the length, if the length of the simple pendulum is increased by 300%, meaning its initial length, the initial length is L, and the final length was actually, when we had the initial length increased by 300%. 300% is the number 3. So it means that the final length is equal to 4L. If the initial length is L and it is increased by 300%, then the final length becomes 4L. Because 300% is 3. So 3 plus the initial one. Please, are we okay with the increase? So the final length becomes this. So for a simple pendulum, T is directly proportional to square root of L. Please, I said if you take T to be equal to 2 pi root of L over G, G and 2 pi will cancel out. So use this. So this is at a T is directly proportional to square root of the length at constant gravity. At constant gravity. If gravity is changing, then it also means that the length must be constant. So there's no need using the formula to get your relationship. So if T1 is this, then T2 will be directly proportional to 4 times L. Okay. Or T2 would be directly proportional to the square root of L2. Meanwhile, L2, which is the final length, is this. So just put 4L. Therefore, when you take the ratio T2 on T1, T2, because that's what we are looking for. We have square root of 4L over square root of L. T2 on T1 is equal to square root of 4L on L, which is equal to root of 4. Now root of 4 is equal to 2. Therefore, T2 will be equal to 2 times T1. Meaning when you increase the length of the pendulum by 300%, the final period would also be twice of T1, meaning T2, the increment in the period, meaning the increment in the period is 100%, meaning this is equal to 200% of T1. So if T1 is this 100% and T2 is equal to 200% of T1, then it means there has been increase of 100%. Please, are we okay? Class, are we okay?
Yes.
All right. If you have any question, ask. Okay, so we got to the period of a simple pendulum last time, and then so that this depends on length of the pendulum, also depends on the acceleration due to gravity. But on the surface of the earth, because acceleration due to gravity is constant, we don't look at its dependency on G because G is constant on the surface of the earth. But if G is taken from planet to planet, or from the surface of the earth and the moon, then we'll have a changing value of G. Okay. Now, another factor. So we are saying T is directly proportional to square root of L. For a simple pendulum, which is something like this, an object attached to a weightless string, the length of the pendulum is always measured from the center of the bulb. So this gives us L. It is measured from the center of the bulb. Not just the length which is tied to this, but from the center of the bulb. Okay. Now, if you sit in a seesaw or in a swing and you are oscillating, okay, if you sit in a swing and then it's oscillating, when you stand up, will it affect the period of oscillation? Somebody who sits in a swing and then oscillates, when the person stands within the swing or in the swing, will it affect the period of oscillation of the person? Yes or no? Yes. Who is sharing something with us? If the person stands in a swing, will it affect the period of oscillation? Yes or no? If yes, why? If no, why? Priscilla, can you try?
Yeah.
Priscilla.
Yeah, I think yes. Yeah. You can hear me.
Yes, I can hear you now.
I think it's a yes because like if you stand in a swing, like your weight will increase. So like it will have more force to move you. So the
Okay. Okay. Natalie, what do you also think?
So please, I also think the same because when you stand on the swing, you are literally putting your whole weight on your legs, which is attached to the seat of the swing. So like it will reduce the rate at which you were going to and fro.
Okay, the answer is yes, but your explanation. If you look at a tall person and then a short person, we are told a tall person, the short person is more stable than the tall person. The reason is that a tall person has, a short person has his or her center of gravity down. The center of gravity is the point where the total weight of the person acts. So if the person is short, okay, the center of gravity is at the center of the body. Now, for a tall person, the center of gravity would be, because he's tall, when we divide his whole body into two, so you realize that the center of gravity, CG, is raised in this case than this one. If you sit in a swing, your center of gravity is where the measurement of the length is taken from. So when you sit within, you have a shorter center of gravity below. Now, when you stand, because you are increasing your height, you would also increase your center of gravity, which will affect the length of the string. So by standing in the swing, you are raising your center of gravity. But the length of the string is always measured from the center of the body. So when we are measuring the length of the string, we will measure it from the center. Meanwhile, when you sit, it is shorter. Meaning that when you stand, okay, you decrease the length of the string. When you sit, you increase it. So by changing L, it will also change the period. Please, is that clear?
No, please come again.
Charlotte, what I'm saying is that when you sit in the swing, when you sit, your center of gravity, where your total weight actually acts, would be below. The length of the swing is taken from the object, which is you, to where it is tied to the support. So when you sit, your center of gravity will be below. The moment you stand, you raise it. So by sitting and standing, you are changing the center of gravity of you, the object. And so it will affect the length of the string. And when the length changes, it will affect the period. Charlotte, is that okay?
Yes, please.
Another factor which affects the period of oscillation of a simple pendulum is temperature. But this applies to strings that are made with wires or conductor, like the grandfather clock. The grandfather clock is a simple pendulum. The length of the pendulum is a wire or a string, a metallic string. So once it's a string, change in temperature would affect the length, okay, by this relation or formula. Any new length, L2, for a metallic conductors, any new length, L2, or let me make it L1, will be equal to L naught times 1 plus alpha times delta T, where L1 is the new length, L naught is the initial length, alpha, we call alpha as coefficient of linear expansivity, coefficient of linear expansivity or expansion. And then delta T is equal to change in temperature. Okay, all that we are saying is that if we have a length of the wire L at a temperature T1, when the temperature changes to T2, it will expand the wire, and so the length will change. L2, meaning L2 will be equal to L1 plus that small change in length, which we are calling as E. Okay, so L1 is the original length. E is that small change as a result of the temperature, change in temperature. Therefore, E is also directly proportional to L1 times change in temperature. E is equal to a constant of proportionality K times L1 times delta T. This constant of proportionality is what we are referring to as this coefficient of linear expansivity. Okay, so K is this L1 times change in temperature is final temperature T2 minus initial temperature T1. But this is what we just refer to as delta T, which is T2 minus T1. So when the length of the wire or the string is a metallic wire, temperature would affect it. So with the grandfather clock is such that when temperature changes, you see it misbehaving. Its accuracy also drops because the period of oscillation, that thing is affected by temperature. Any question? No question. All right.
Oh, sir,
Today,
please, sorry, sir, please, the L1, if L1 is the initial length, is it the same as the L naught?
yes, either you use
Okay.
L1 or L0.
Okay.
I think I'm using both.
Yes.
No, it's either L0 or L1. So I can change. You see here I use the final length as L1 and initial length as L0. And here I'm using the initial length as L1, final length as L2.
Okay.
So if it is grandfather clock, this is how excursion. This setup I have in my hand is what we call as a loaded or helical spring. When I exert a force to cause this to displace, it will oscillate. The repeated up and down motion of a body about a mean point. Okay, so this is what we call as a loaded spring. So the motion of a loaded spring or helical spring is an example of simple harmonic motion. This is an example. So the motion, that is what we are coming to do for today. Motion of a loaded spring or helical spring. The motion of a loaded spring or helical spring. Oh, okay. Before, let me connect what we've just learned to if there is a change in temperature. So if the string is a metallic something, T1 will be directly proportional to L1. T2 would also be directly proportional to L2. Therefore, T1 on T2 or T2, since we want the new, would be equal to square root of L2 over L1. Now, what is L2? L2 is given by L1 times 1 plus alpha delta T over L1. And so this and this will cancel out so that you have square root of 1 plus alpha times the change in temperature delta T. So it means if alpha is given, if change in temperature, maybe initial temperature and the final temperature will be given, or the magnitude of the change in temperature will be given to you. So that the new temperature period T2 becomes T1 times the square root of 1 plus alpha delta T. So simple. So, but this works when the string is a metallic wire in grandfather clock. Okay. Do I clean the board? Hello, do I clean the board?
No, please.
I was coming to call you, Charlotte.
Please, you can clean it now.
So the period of oscillation of a helical spring or a loaded spring, we are saying that is also an example, one of the examples of simple harmonic motion. The motion of the loaded spring. Okay. So we want to see if truly that is also SHM. The motion of a loaded or helical spring. So we have a spring. When there is no load, this is the spring. When you exert a load on the spring, the load is stretched. This line is the equilibrium position. Now, if we want the spring to oscillate, we give it an amplitude of oscillation. And this is now the object. So we have this line indicating the mean point or equilibrium position, where there is no external force acting on it. And class, this is the situation I'm referring to. When there is no load suspended on the string, this is it. So this, what we have the diagram A, B, and C. The diagram A refers to this, when there's no load. The diagram B refers to when a load is suspended. Let me take off some of the load to reduce the extension. So this is A. This is B. Then C is when I give it a certain amplitude of oscillation, either up or down, for the body to oscillate. Don't forget at B, the body is stationary. There's no motion. But at C, I'm giving it an amplitude of oscillation. And that will further, and look at something. The load is stretching the wire, extending it. So this is the actual length of the wire if there is no load. Okay, let me still take some of the masses off. This is the actual length of the wire, about 2 centimeters. When you suspend a load or weight, it stretches it. The reason for which you see this uncoiling, this length to be greater than this. Please, are we following? The reason for which you see B to be longer than A. Now, C is also longer than B. The reason is that because I want it to oscillate, I give it a net force in one direction, either up or down. So giving it an amplitude of oscillation will further stretch it. And set it into oscillation. Please, are we okay? Are we okay?
Said yeah.
Hello.
Hey, so does it mean that with the C you didn't add any mass, but then you just
We still have the mass.
oscillated it and that
Charlotte.
caused the increase in
Charlotte,
the height.
B, this is B. And C, I exert load or weight or force on it. And the force is, by giving it that force, you are giving it a certain amplitude of oscillation. So I'm not adding any load, but because of the force acting on the body, it will further stretch it. Okay.
Yes,
to give
please.
it that amplitude of oscillation. So when I move it to this direction, to this point, from here to maybe this point, and leave it, it will move up and down, okay, between where I stretch this to and the other end. So when I leave it, look at it. Is that clear?
Yes, please. Thank you.
Okay. Now, springs work on a particular principle. And this is it. They work on Hooke's law. Hooke's law. Hooke's law applies to any elastic material. And Hooke's is saying that if you have any elastic material and you exert a load or force on it, if you don't extend or exceed the elastic limits of the material, the load exerted will be directly proportional to the extension. I'll give you the definition. But all that Robert Hooks is saying is that this is an elastic material, meaning it can be stretched, we can exert a force, and when the force is exerted, it must be able to regain its original shape or form. Elastic materials have that characteristics. Now, springs are identified by that they are spring constants or force constants. Now, the spring constant or the force constant, spring or force constant, determines how rigid or stiff, determines how rigid or stiff springs are. If a particular spring is so rigid, then it means it has higher or larger value of spring constant. If a particular spring is loose, then it means it has lower value of spring constant. And this constant, spring constant or force constant, is represented by the letter K. Spring or force constant is represented by the letter K. So if you look at the springs used in cars, the springs used in machines, these are very hard or rigid or stiff springs, and they have huge or large value of K. This one is loose. Okay, so the value of K is also less. So the numerical value of K determines how rigid or stiff springs are. I hope you are following.
Yes,
From
please.
Abba to Yaba. All right. Now, Robert Hooke is saying that if you have a spring and then you suspend a load or a body to it, this is the load suspended. Robert Hooke is saying that if you don't exceed the elastic limits, meaning that if you don't go beyond how this must be stretched. The elastic limit okay, is the lower or upper limit by which you can extend or stretch the elastic material. If you don't go beyond the elastic limits, what the spring or the elastic material can bear, okay, then the load, the magnitude of the load or the force or the weight, the load or the force exerted by this or the load must be directly proportional to the extension in the spring. So F is the force or the load, magnitude of the force or the load, and X is the extension created by this. So if I suspend one, of these masses are 100 grams. If I suspend 100 grams, look at the extension it is producing. When there's no load, this is the length of the wire or the spring. When there is load, look at the extension. Now, as you increase the load, the extension also increases. Hooks is simply saying that if you don't, there is a limit to which this can be stretched. And if you don't exceed that limit, then the load will be directly proportional to the extension. But the moment you exceed this body or the spring fails to regain its original shape. Once you are within the limits, when the load is removed, you can always get the original shape or form. But the moment you stretch it beyond its strength, and this is what we are calling as elastic limit, when you leave it, the spring cannot regain its original shape. And this is what we call, or we are referring to as Hooke's law. So Hooke's law is defined as provided the elastic limits of a material, and here we are referring to elastic material. So I'm giving you Hooke's law. Provided the elastic limit of a material is not exceeded the extension is always, or is, the extension is directly proportional to the load. So provided the elastic limit of a material is not exceeded, the extension is directly proportional to the load. Okay, so when we compare this spring is given, when the load is suspended, is given the extension X. Mathematically, Hooke's law is stated as the force exerted is directly proportional to X, where F is equal to the load or the force attached, and X is equal to the extension. How the material got extended is what we are technically calling as extension. So for any direct or linear proportionality, when you introduce an equal to sign, there is a constant of proportionality, K. This constant of proportionality, K, is what we are calling as the elastic limit. Sorry, the spring constant. K is the spring or force constant. And this relation is what we are calling as Hooke's law. Now, in Hooke's law, you see a minus kx. The minus sign indicates that the force acts in one direction and the extension is also in the opposite direction. Okay, now you understand this minus very well as we continue, but from what it looks, this is it. Let me exert a force on the spring. So this is the direction of the force or the load. But then, you see, when you oscillate this, if I want this to oscillate, and then I suspend a load, you see it is oscillating. The extension acts downwards, and there is always a restoring force in the opposite direction. Look at it again. I want this to oscillate. So when I exert the force, which is the load acts downwards, but you see the load acts downwards, and you see a restoring force acting, okay, against it, trying to restore the object, the spring, to its original shape. So the extension is in one direction, and the restoring force, which is also equal to the weight or the load, acts in the opposite direction. So you exert a force, okay, the extension is down, but there's always a restoring force against it, whose magnitude is the same as the amount of the load suspended. So here we are looking at the force, the direction of the force, which in this case is the restoring force, because the restoring force is equal to F restoring is equal to the weight or the load suspended on the spring. So the restoring force acts in one direction, and then the extension also acts in the opposite direction. Then I'll go ahead.
Okay, so please, can you illustrate the F equals positive kx if you just illustrated a negative?
Come again.
Please, can you illustrate with the spring F equals kx?
You see, and that's what I was doing. This
So you
is
said
Go ahead.
so you said you were illustrating the one where the force is in the opposite direction and then no, the force is in one direction and the
Okay,
extension
so
is in the opposite direction.
Hooke's law. Hooke's law says that the load or the force is directly proportional to the extension by a magnitude amount. Now, the same Hooke's law, if we want to include direction, okay, for an oscillating body, I said that whenever a body is suspended to an elastic material and made to oscillate, the direction of the extension, okay, opposes the direction of the restoring force. If it's like this, it's not oscillating, it's at rest. Now, if I exert a further load, then you will see it oscillating up and down, okay? Meaning that the extension, when it is oscillating, the extension is down, but the restoring force, whose magnitude is the same as the load, acts against it. So whilst it oscillates, there seems to be a force which always tries to restore it to its undisturbed shape. Okay, so there's a force pulling it up so that it always regains its original shape. This is Hooke's law. Della, are you okay?
Yes, sir.
All right.
Thank you.
So this is Hooke's law. The helical spring, okay, works on the principle of Hooke's law that provided the elastic limit of the material is not exceeded, the extension is directly proportional to the load. The moment you exceed its elastic limit, this relationship will not be there. And we have a lot of practical applications. So a load suspended on a spring, if this is made to oscillate by giving it an extension, it was like this. It was like this. So when the load is suspended, the object is extended by this amount, E. The restoring force, which always tries to restore the object back to its equilibrium position, O, always acts against the direction of extension. So extension, it's in this direction, downwards. Extension E is in this direction. And then the restoring force, F restoring, is in the opposite direction. When the spring is compressed by compression, then you realize the extension is or the compression in the opposite direction, then the restoring force acts in the opposite. So this is extension, and this is when we have compression. The extension and then the restoring force are always opposing, and that is Hooke's law. So for a body oscillating, the net force causing the oscillation of the body is by Hooke's law. The net force is by Hooke's law. Which is F is equal to minus Kx. So for an oscillating body extended by X, if the net force or the resultant force causing the oscillation is Kx minus Kx, then every net force or resultant force causes acceleration of a body. So we are interested in the acceleration caused by the net force, caused by this net force. Please, are you with me? So for an oscillating body, the net force responsible for the oscillation or acceleration of the body is given by this F net or F resultant. Now, every net or resultant or unbalanced force causes acceleration. So what is the acceleration produced by this? By comparing this to Newton's second law, force or every external force is equal to the mass of the body times the acceleration. So we equate ma to minus kx because they are all forces. And when we make A the subject, we have the acceleration of the body. So when I suspend this and causes this to oscillate, the acceleration of this body is determined by the spring constant K, which is how rigid this is or loose K. So different springs have this constant values. So knowing the K of this and then the extension provided when this load is suspended divided by the mass of the load gives me the acceleration of the body. So K is the spring constant, X is the extension. No, if the body is accelerating not due to gravity. Okay? Because look at this. Akuya, is the body accelerating?
No, please.
Akuya, is it accelerating?
No, sir.
Is there gravity?
Yes, sir.
Yes or no, Akuya?
Yes, please.
Yes. So once the body is not accelerating, yet there is gravity. Meaning when there is an external force causing the acceleration, it should tell you that then this is not due to gravity. It's by the acceleration of the body. Right?
Yes, please.
So the acceleration, and don't forget the acceleration is the movement of the body. Change in speed. Before, the speed was 0. Now the speed is not 0, increased. So the difference in the velocity with respect to time gives us the acceleration, which can be determined by K over M times the extension. Natalie.
So does that mean that the acceleration is directly proportional to the extension and
But
then inversely?
fine, yes. You see, what it means is that you can say that the acceleration is directly proportional to the extension, but on condition that you vary the masses, the mass suspended, meaning this is it. And look at something. It's a good question you asked. If I suspend one of these masses, look at the acceleration of the body. Okay, so fast. Let me add another one. And then displace it. A bit slow. If I add another one, and then cause it to oscillate so slow. So the relationship is that A is inversely proportional to the mass or weight. When the mass increases, acceleration decreases. And that is what we've seen here. Natalia, are you okay?
Yes, sir.
All right. So A is equal to this. A is equal to this. Now what something clearly? If A, the acceleration is equal to minus K over M, then K is constant. So long as we are not changing the spring, this value of K is constant. The mass can always be determined. If you even do not know, you can use a weighing balance to determine the mass. So we refer to this ratio as a constant. So K over M is equal to a constant. Therefore, if this ratio is a constant, then we can say that A is equal to a big K times X. And so there's a minus. We can therefore conclude that, okay, then A is directly proportional to minus of the extension or the displacement in the position of the body. And this confirms that the motion of the helical spring is simple harmonic motion because its acceleration is directly proportional to the displacement from the mean position. And let me redraw this for you to see something. When there's no load, this is the length of it. When there is load, the string, so this is the equilibrium position, is stretched by this amount. X, this is the extension. So the acceleration of the body, which is always against the direction of displacement, is directly proportional to the extension, signifying that this motion is simple harmonic motion. Please, any question? All right, then let's look at the period of oscillation of a loaded spring. Period of oscillation of a loaded spring. The period of oscillation of a loaded spring. Just as we determined for simple pendulum. As for simple pendulum, its period is equal to 2 pi square root of L on G. What is the period of oscillation of a loaded or helical spring? The acceleration of a helical spring is given by this. minus K over M times the extension. And what's the general acceleration formula of a body executing simple harmonic motion? What's the general acceleration formula of a body executing SHM?
Negative omega square x.
Pardon?
Negative omega square x.
So minus omega squared x. So when we compare, omega squared is equal to K over M. Omega is equal to K over M, square root of K over M. Therefore, we know omega to be 2 pi on T. Help me make T the subject. Help me make T the subject. Charlotte,
Yes, please.
help me make T the subject. Charlotte, are you there?
Yes, please.
I'm waiting for you.
I think you reciprocate it and you make 2 pi the denominator.
Eti, give me the
then-
final value.
Okay, you get 2 pi root of M on K.
Thank you. So very, very similar to that of simple pendulum. Look at it. 2 pi M on K. Meaning the period T is directly proportional to the mass. The period T is inversely proportional to square root of the spring constant. This is at constant K. And then at constant mass. So for two different masses, there must be two different periods of oscillation. So T1 over T2 must be equal to square root of M1 over M2. Then for two different spring constants, oh, I should have come here with different springs to demonstrate this for you. Another time will do. So for two different spring constants, T1 is inversely proportional to 1 on root of K1. T2 must be 1 on root of K2. Therefore, help me make T1 over T2, take a ratio of T1 on T1 on T2. Do that for me and then tell me the final output. Inshira? Inshira?
Yes,
Inshira
it's
Bada?
there, yeah.
Help me do that. T1 over T2. What will that be?
Miss Lydia, please, I just got up. So I'm a little lost.
Okay. Then, Lynn. Lynn. Lynn, are you there?
Yes, please.
What is T1 over T2 from when we have different spring constants?
Please, K root of K2 over K1.
Okay, 2 on K1. Yes. For period of oscillation of a helical or loaded spring, there is also an infamous relation, which is also used. And this is it. You see, when the loaded spring is at equilibrium, this is what I mean. If I have this and it's here, when it's oscillating, this is how it looks. When it is at equilibrium, then the position is still. When it is at equilibrium, it means that the net force acting on this is equal to what? Zero. Good. Meaning that the restoring force is balanced by the weight. But when it is oscillating, then it means the restoring force is greater than the weight. It cannot be the weight being greater than the restoring force. Restoring force is greater than the weight. But when it is stable, like this, the restoring force is balanced by the weight. So, if at equilibrium, we have the restoring force Kx, Hooke's law, by magnitude is equal to mg, the weight. Then, if you make a ratio of m on k at one side, m divided by k at one side, we have this being equal to x on g. The extension in most books is represented by E. So if you see E is the extension. And because M at equilibrium, M over K is equal to extension over gravity, the period of oscillation is also in some books expressed as 2 pi root of M over K. This is M over K, which is equal to 2 pi times the root of E over G. So when you see it written as this, it is from considering the equilibrium position of it. Please, is that okay?
Yes, please.
Now we don't use this formula so much here because on the surface of the earth, gravity is constant. It doesn't vary. if we are looking at from one, okay, planet to another planet, then we can cater for this. But so long as we find ourselves here, J is constant. So for one spring, the period of oscillation is equal to 2 pi times the square root of m over k. Any question before we continue? Amma, any question? Natalia, any question? Ekuya?
Mr. Yeah.
Amma, any question?
Yes, please.
Ask. Let's not waste time.
Mr. Yeah. Hello.
Hello, Amma, I'm listening.
Mr. Yeah, please can we classify the restoring force as tension?
Oh, you can say tension, which restores. A tension is a force. Okay. So there's nothing wrong if you
Yes, please.
describe the restoring force as tension. But usually
Okay.
we talk about tension in, well, elastic materials for which the spring is one. So it can be taken aside. Natalie,
So please, can the value of the extension be quantified?
oh yes, we
Okay.
can measure it.
Okay.
You can always measure it. And this is it. Look at what I have here. This is a spring. I can measure I can measure its original length. Okay.
So in a like if you are given a question and then let's say you're supposed to use that formula, can you be given the value of the extension to find a
Oh
period?
yes. Oh yes. I'll be solving examples with you.
Okay.
Okay. Now, if we have two springs, the story is a little different. Grace, are you there?
Yes, please.
Ekwe, are you there? Adoma?
Yes,
Carl? Tucci? If we have two springs in series, this is K1, K2, meaning they are of different rigidity or stiffness. There's a story of two springs connected in series, or can be also be drawn as this. So K1, K2. We have two springs. When a load is suspended and set into oscillation, what happens? So when two springs are arranged in series and then subjected to by a load, same force same force acts on them. So here it is the same force F which is acting on these ones, but they will be stretched differently because they are not of the same spring constant. Don't forget the spring constant determines how stiff or loose springs are. So if we have the same force acting on all of them, but the K are not the same, then clearly they will be stretched differently. Please, is that okay?
Yes, please.
So when two springs are arranged in series and same force acts on them, they would be stretched differently. But the same force would act on them. So if I want to determine the extent of stretch or extension in this spring K1, by Hooke's law, F is equal to Kx. So X1 would be equal to the same force F divided by K1. The same force, if I want the extension in this other one, then X2 would be equal to same force F divided by K2. Therefore, total extension X total would be equal to X1 plus X2. What is X1? X1 is this, F over K1 plus X2, F over K2. Therefore, total extension XT is equal to, I can factorize out F1, F. So I have 1 on K1 plus 1 on K2. Let's divide through by F. Now from Hooke's law, if we have X total or X divided by F, what is it? From Hooke's law, what is X divided by F? Oh, from Hooke's law, what is X
The
over
inverse of
the inverse of what?
K.
Good. So this is the inverse of K, meaning is the inverse of K total. The inverse of K total is equal to 1 over K1 plus 1 over K2. What this means is that if you have two springs connected in series, you must find the total spring constant. So the total spring constant will certainly be equal to, so if we are making K total the subject, this will be equal to K1 times K2 over K1 plus K2. What we've done here is that if I have two springs connected in series made to oscillate, and I'm asked to find the period of oscillation of the two springs combined. We just saw that T, the period of oscillation for a spring, T is equal to 2 pi over M on the spring constant K. Meaning, if I have two springs, then this K must be the total spring constant of the combined springs. Therefore, for two springs connected in series, the period of oscillation T would be equal to 2 pi times M over yes, I want you to finish it and tell me. So in effect, this is what I'm saying. For two springs combined, it will be M, one mass. Don't forget we have one mass. This is M. But the K would be the total spring constants. Okay, so this must be M over KT. So substitute whatever we had for KT into this and tell me the final results. Do it, and then I'll call one of you to share it with us. I'm going to get your question so we can apply. Hey, so what have you had for T? Akwiadoma, what did you get for T?
T is equal to 2 pi root of m multiplying k1 plus k2 all on k1, k2.
So, okay, so 2 pi I'm multiplying K1 plus K2 all on K1 times K2. Okay, let me see if what you are saying is true. Okay, you are correct. In fact, you are just saved by the bell, and that is my earpiece is giving me the signal that it has dissipated the total energy in it. So it means I have to go. But I've taken short of some questions, which I want you to try. Okay. So I'll send it to you right away so that you just try. It's unfortunate. It's unfortunate. I don't know why these days my earpiece just leaves me on the way. But I also felt we had done a lot of calculations, so I think it will be better if we solve one or two questions. But unfortunately, it will go off anytime soon. So class, I will send the questions to you. Just try it, okay? It is even gone. I'm coming. Good. So I'll send the questions. Please try it and then you get back to me. Okay. Please correct whenever you are giving work, the intent isn't that get everything right. I want to see how you apply whatever we learned in solving problems. So just do your part. If but the point is, I cannot hear you when you speak. That's the unfortunate thing. So whenever I give you work, just do what you can. If you could, if you are giving 2, 3, and you could answer 1, just do it. Send it to me. I mean, because it's a learning process. Okay, I don't expect you to get everything whenever you are giving. So do not hesitate in solving questions. Give it a try and let me get feedback from you. So I've taken short of about 2 questions. I'll forward it to you so you try and then we discuss it. Okay. Of course, I'll mark for you. Okay. So unfortunately, we have about about 15 minutes to go. But I'll give you the time to work on the assignment I'm going to forward to the group now. Do it and let me hear from you. Okay. So we haven't closed. I'll still be waiting for your assignments. Please stick to it. Until then, bye-bye. Take care of yourself.